Okay, we're going to go ahead and finish up this chapter with reviewing a few example problems. So let's go ahead and look at this first one here. We have it's written to evaluate the performance of an alternate energy technologies AE21E solar collector on January 21st if the collector is located at 32 degrees north latitude and tilted at an angle of 32 degrees. The water inlet temperature is 58 Fahrenheit. The ambient temperature varies from 25 Fahrenheit at 8 a.m. to 45 Fahrenheit at solar noon, 35 Fahrenheit at 4 p.m. Metrics of interest include the hourly efficiency, the hourly solar energy collected, and the percentage of incident solar energy collected. So if we go back to our alternate energy solar collector here, we can pull out some of the data that we need, starting with the gross area. So we'll look at the area, 20.73 feet square feet, and we can pull out also the intercept, which is 0.66, and our slope, which is negative 1.23 BTU per hour per square Fahrenheit. So let's go ahead and take note of those three parameters. So we have the area, we have the intercept, and then we have the slope. So with these, we can go ahead now and start looking at our performance. So we can go ahead and we're going to go ahead and evaluate this and put it in a matrix form since we're looking at hour-to-hour performance here. So we have, for example, the temperature, right, is going to be 58 Fahrenheit for all of time. So starting at 8 a.m. all the way to 4 p.m., our temperature of the water going into the collector is the same. Our ambient temperature was given to us to be 25 degrees Fahrenheit at 8 a.m. and it incrementally increases to 45 degrees at solar noon. So I'm just going to go ahead and increment that linearly. So 30 at 9 a.m., 35 at 10 a.m., 40 at 11 a.m., 45 at noon, and then incrementally decrease it until it hits 35 degrees Fahrenheit at 4 o'clock in the afternoon. So that would give me 43 degrees, 41, 38, and 35. So again, that's in degrees Fahrenheit. And then what we'll need next too, in order to evaluate this, is looking at the solar insolation. So if you were actually to go into your books, right, you can go and find for a location of 32 degrees north latitude, which is what this problem statement is asking for. And we can go ahead and look at the solar insolation for January 21st. And it's looking like it's at a tilt angle of 32 degrees. So starting at 7 a.m. it's 0. Then 8 a.m. we have 106. That's in BTU per square foot. Then 193 for 9 a.m. and following 10, 11, and 12 a.m., 10, 11 a.m. and noon, it would be 256, 295, and 308, and then counting backwards until you hit 4 p.m. again. So with that said, we can go ahead and we can list out our solar insolation values. And again, this is in BTU per square foot. So continuing on, we can look at what our hour-to-hour efficiency is. So the efficiency would be equal to the intercept minus the slope multiplied by Tn minus T ambient over the solar insolation value. And these values change hour to hour. So you would get an hour to hour change of efficiency to be the following. Then what you could end up doing is you can actually compute, I'm not going to go through all the math right now, but you can compute what the useful energy that you would get over the course of the day, which would be the collector area multiplied by the incident radiation multiplied by the efficiency. And what you can do is once you get this number hour to hour, well, you can just go ahead and add it up, right? And we're basically where you sum the useful energy multiplied, and assuming that for each hour to hour, that value, right, is going to be valid for the course of an hour. So you would end up, if you do the right math and conversions, that during the course of the day, you can get 6.76 kilowatt hours worth of total useful energy out of that solar collector. And then the overall efficiency would be the sum of the hour-to-hour useful energy over the sum of the incident solar insolation. And you would get that the overall efficiency over the course of that particular day would be about 55%. So I'm going to go ahead and in this last part of the video, I'm going to cover something called the F-chart method. Now you have a homework problem where you have to do this, and obviously you're going to want to use Excel of some sort in order to be able to complete this. Specific instructions are in the homework assignment, but I wanted to go and look at a way for estimating the monthly heating load. What we just looked at is the example of a day. What is the overall efficiency or the usefulness of the solar collector for a day? But what about if you're trying to do a yearly analysis, right? It gets to be pretty complicated. So there's this method called the F-chart method. The F-chart method provides a procedure for estimating the fraction F, the fraction of the total monthly heating load that can be supplied by an active solar energy system. So the correlation was derived from the results of a large number of hour-by-hour solar energy system simulations. The two parameters are the ratio of collector losses to heating loads, X, and the ratio of absorbed solar radiation to heating loads. So the F-charts have been developed for three basic system configurations. One is for space and water heating using water as a medium, which is the specific one that we've been looking at in this textbook. Two other ones are for space and water heating using air as a medium, and then also another one would be for process hot water. So here's how it works. Here's a schematic of a quote-unquote standard system configuration using a liquid heating transfer medium. You have basically the collector, you have the collector storage heat exchanger, and a system that's set up to use the energy collected from the collector to basically use water to heat a house, along with some auxiliary systems to supplement what the solar collector can't do. To analyze this, we're going to use the F-chart method, and this is how the F-chart method basically is detailed. So again, detailed simulations of that system illustrated in the figure we just looked at were used to develop the correlation between two dimensionless parameters, X and Y. And those two dimensionless parameters are used to compute F, which ends up being the monthly fraction of the heating load carried by the solar collector. The two equations are listed here. X, again, is the ratio of the collector losses to the actual load. So you have the collector losses divided by the actual total load. And that is a function of several parameters. It's a function of the collector area, a function of the corrected collector heat removal factor, which is usually taken as 0.97 times the heat removal factor, the collector loss coefficient, the monthly average ambient temperature, the total number of hours in a month, and then the monthly total heating load. And then Y is the other non-dimensionalist factor, which is basically the ratio of the absorbed solar radiation to the total heating load of the building. And that is a function of T alpha, which is the monthly average product of temperature versus, transmissivity multiplied by absorptivity. It's usually taken as 0.96 times the actual transmissivity times absorptivity. And then HT, which is the monthly average daily radiation incident on the collector surface. And then N is the number of days in a month. So these two equations are pulled together to compute that factor, that monthly solar fraction F. So for liquid systems, again, this is the final correlation for liquid systems. And then there's a similar relationship that's been derived for air systems. So you can see sort of here is a plot of the solar parameter y versus the loss parameter x as a function of the fraction. What I think I'm going to do is skip forward to an example problem. I'm not actually going to write in anything in this example problem. It's all laid out. But this example problem is very similar to one of the homework problems that you're going to be completing for this chapter. So let's go ahead and look at this. So the problem reads, an office building in Meridian, Mississippi is to employ an alternate energy AE 21E flat plate solar collector for space and water heating. The collectors will be mounted facing south, and the estimated monthly load is provided in the table before. So the table shows the monthly heating energy requirements for an office building for each month of the year, January through December, and it gives you the load in megajoules. There are thousands of megajoules. So for example, January is 140,000 megajoules, February 120,000, so forth and so on. So the solar energy system is to provide all the water heating requirements for the summer months and a yearly solar heating fraction of 60%. So that's the requirements that they want. They want the system to be able to provide all of the water heating requirements for all the summer months. And then over the course of the whole year, they want this system to provide 60% of the total heating needed for the building over the course of the year. So the first part is asking how many of these solar collectors are needed to meet the specification. Then it says if natural gas costs $10 per million BTU, how much would be saved by the installation of this solar system? Right. So let's go through each step. First step, you can see you would basically define the month in terms of days, right? So you have a matrix here starting from January down to December. Just indicate the number of days in each month. Following that, you would look at the monthly average conditions from the NREL. It's a website that has a lot of the weather data. You look at the location of, in this case, Meridian, Mississippi, and you would find that you have the radiation over the course of the day, the daily radiation, sorry, for that month, and the so that would be this matrix here. Then you'll have the total load that the building requires. This is from the table in the prior slide. And then the ambient average temperature for that month, right? Starting from January all the way to December. Next, you would compute your X parameter and Y parameter, again, on a monthly basis. And then you can actually go ahead from there and calculate what your fraction load is, knowing that for the summer months, in this case, May through September, that you wanted 100% of your monthly fraction to be, you want 100% of the total water heating requirements to be provided by the solar system. And what's interesting is that as you set up your Excel spreadsheet for this, or MATLAB, whatever means you want to use, you can actually leave the number of solar collectors as a variable that you change until you get what the numbers that you want, right? Obviously, the number of collectors has an effect on the total area. So you take the number of collectors multiplied by the area per collector, and that gives you the total area of all of the collectors added together. And what you end up doing is if you can go ahead and take the you can also compute the percent over the course of the entire year, what percent of the total heating load that the solar collectors have over the course of the year. And you can actually quantify that by averaging out the matrices by multiplying the by the number of days of the year, right? So basically, you would take the load from the solar collector and divide it by the total load over the course of the year, right? And then you would get your percentage. And then you can use those numbers based on the cost of gas and look at the total savings. In this case, a yearly savings would be about $4,000. I tried my best to detail this out, how it's solved, so that you have something to follow when you're doing the homework assignment related to this type of question. Okay, that pretty much ends this final video for a chapter on active solar systems. Of course, you're going to